Hi, today we are going to present the final project, Torsion bar, exposed by my colleagues Gustavo, Andrés, Ruano, Hoyos, Eduard Santiago, Reina, Narváez, Juan David, López, Andrade, and me, Valeria, Rincones, Arellano. Introduction. The Runge-Kutta methods are the numerical resolutions set for the initial value problems using greater amplitude. Its importance lies in the fact of being able to build numerical methods of great precision and accuracy that do not require the calculations of high order derivatives. In this work, we implement the Runge-Kutta methods for the orders 2, 3, 4, and 6 using the Python programming language. We obtain a tool that allows us to obtain estimates and calculate their error with respect to the exact solutions, and therefore it can be used for the learning teaching of these numerical methods. A general objective is study the behavior of a steel bar subjected to torsion that is made by means of graph of the derivative of the angle with respect to time.
Problem statement. One of the current situation of construction rotting when an external moment occurs about a longitudinal axis apart that predominates in the rod where it generates a torsion effect.
Methodology. For the development of this code executed in Google Colab using the Runge-Kutta method, the aim is to analyze and graph the curve according to the initial conditions that are going to the work on. For the point A of the exercise, the first step is to write the specific of the first order differential equation by means of a function and then determine the value of the variables with which you will use the for each condition. There are some that exercise give us, others the which are take arbitrarily, and finally choose that they be calculated using the data offset offered by the statement. On the formula that we will use to calculate the moment of inertia of the rod is following: mass multiplied by square leg divided by 3. At this point, as we use the work with the differential initial condition, we will carve out their different section in which we will enter the variables in which the conditionals that the workshop adds for will be changed. For point B, there give us the value of the angular frequency, and thus we will obtain the value of the torque with the following formula: cosine of angular frequency multiplied by time. In the code that follows and the result for each section, the final values and their respective graph, and the observed according to the conditionals and variables.
Results. For point A, and after considering the moment of inertia of a thin rod of length L equals 1 meter and mass m equals 2 kilograms, the elastic constant K for steel and iron, the torque T by T equals 0, and barring the values of the angle theta and time, the results at point A are as follows, that you can see in this part. In the first one, the main change is the range, but the other is really important too, because the change in W modify other variables like K, barring the graphics. Despite the above, all the graphics have a similar design. For point B, and after considering the moment of inertia of a thin rod of length L equals 1 meter and mass m equals 2 kilograms, the elastic constant K for steel and iron, the torque T by T equals cos per w per t, where w equals 1, and using three different values for the angle theta and time, the graphical results at point or of point B are as follows. In this second result, the most important change is the main code is the range. The other changes were produced in the graphic code, but in general all the graphics preserve the same base. A conclusion, Runge-Kutta 4, which is a useful iterative generic method, explicit and implicit, of numerical resolution of differential equation, it is very exact in the development of these and other equations, since it allows the data of the problem to be varied in a relatively simple way and expresses the results clearly. Thanks.